welcome back. This is the fourth and final part of this very long lecture about variables and forces in the Earth's atmosphere. And again, as we go through the book here, we're hitting our next force being the force of gravity. It's sometimes a little bit of a surprise to like ATS 113 students to find out that gravity affects the atmosphere, but air has mass. We talk about like how many kilograms per cubic meter the density of the air is, so obviously air has a certain mass in kilograms. The Earth has gravity, and therefore the atmosphere is attracted towards the center of the Earth by just the forces of gravity, you know, as in described by good old Sir Isaac Newton. And that's usually about where we leave it in the context of like ATS 113, but because this is the kind of the only earth sciencey type course you're going to have about this kind of stuff, I want to show you that actually gravity in terms of how it affects, well, any object, but especially the atmosphere, is, well, frankly, somewhat more complicated than that. See, I got a little guy here standing on the surface of the Earth at some location. And if you're at some location on the surface of the Earth, we all know which way gravity is pulling. Gravity is pulling us down. That's what down means. It's the direction something would fall if you dropped it or whatever. And you would be forgiven for assuming that, like, that would lead to, like, if you could just follow that motion all the way down, it would lead to the center of the Earth. Like the way that yellow arrow is going towards the, I guess it's yellow circle I put there at the center of that globe there. But you would be wrong. Actually, if you, like hung a plumb bob and looked at which way the string was pointing, if you could just follow that all the way down, it will not pass through the center of the Earth. Down is not towards the center of the Earth. It's in a slightly different direction that has importance in like earth sciences and atmospheric sciences and so on. I'm not sure entirely in wind power, but since your book is mentioning it, I may have missed it when I looked through the future chapters, but I think we need to talk about it since your book is talking about the fact that gravity is not pulling towards the center of the Earth, it's in a slightly different direction. And that's because when we talk about gravity, strictly speaking, we're not talking about what Sir Isaac Newton was talking about when an apple fell on his head. That's Newtonian gravity, objects being attracted towards the center of each other. But when we're talking about gravity, we're talking about apparent gravity, where it's a combination of that kind of Newtonian idea about gravity, plus other forces that are at work when objects are at rest, and one of those is a centrifugal force. I mean, even an object that's stationary on the surface of the Earth is actually moving pretty quickly. Once every 24 hours, it's going all the way around the axis of the Earth. And therefore, there is a centrifugal force involved. As the object rotates around the axis of the Earth, you get a centrifugal force equal to omega, that's that rotational rate of the Earth again, times r squared, where r here is not the distance from, like the radius of the Earth, it's actually how far you are from the axis of the Earth. It takes a little bit of trigonometry to figure that out. So this is going to create a centrifugal force on objects that are just sitting there at rest. Look around you in your room right now. There are objects at rest? No, they are not at rest. They are going around the axis of the Earth on a journey every 24 hours, therefore they have a centrifugal force. And so there is a Newtonian force of gravity pushing in towards the center of the Earth, but there is a centrifugal force, which I have labeled there with that blue arrow, pointing away from the axis of the Earth. And it's kind of in a weird direction. It's not from the point of view of the guy on the globe there. It's not towards the center of the Earth, it's not straight up, it's away from the axis of the Earth. Again, figuring out the exact angle of this would require knowing its latitude and doing some trig, and we're not going to do that right now. But the point is, the apparent gravity is the combination of those two effects. It is a combination of the gravity, the actual Newtonian fundamental force in the universe kind of thing, where it's pulling the object down towards the center of the Earth, plus the centrifugal force caused by the rotation of the rate of the Earth, and so on. So this is what, when you experience gravity, what you're actually experiencing is the combination of those two forces, and same with any object, including the atmosphere. The atmosphere is actually responding to a force of gravity that is not exactly in the direction, it's an apparent gravity, it's not exactly in the direction of like the center of the Earth. And this has consequences that are fascinating in like atmospheric dynamics 1 and 2, ATS 571 and 572, but that's not where we're going with this right now. The main role that gravity, actually apparent gravity, plays in the Earth's atmosphere is not so much to affect the winds as to kind of set up the structure of the atmosphere vertically. Because it's going to be perfectly balancing the vertical pressure gradient force. What am I talking about when I say the vertical pressure gradient force? Remember, gradient was how something changes over distance. A vertical pressure gradient force would be how pressure is changing vertically. Well, we learned early earlier in this lecture, actually, that pressure always decreases with respect to height. In fact, it decreases pretty fast with respect to height. And therefore, as we go up in the Earth's atmosphere, we're always headed towards lower pressure. Doesn't that mean that some volume of air that's parked right here is experiencing a vertical pressure gradient force, pushing it from the higher pressure down here at the surface towards the lower pressure up above? Yeah, absolutely. In fact, it's a very, very large force, a very large vertical pressure gradient force. As it happens, it is perfectly balanced by apparent gravity. There's a force of gravity pulling the air parcel down. Oh, watch out, I just gave a scary word there. That volume of air pulling it down towards the ground is exactly, the gravity pulling it down exactly balances the vertical pressure gradient force putting it up. That's actually an important phenomenon in the Earth's atmosphere called hydrostatic balance. Hydrostatic balance is this feature of the atmosphere that kind of helps define its structure, the rate at which pressure changes with respect to height and so on, because the vertical pressure gradient force has to be perfectly balanced by the force of apparent gravity. Now, I want to draw your attention to that word I kind of just dropped in there, and it's actually circled there in yellow there, air parcel. I've actually slipped up, I think, and used that term a couple times over the course of this lecture and so on. An air parcel is an idea that we use in atmospheric sciences. Think a bubble. Think a balloon, something like that. A volume, a small volume of air that we can do things like analyze the forces that work on it or so on. Now, that's an important vocabulary term. Depending on if you took things like ATS 113, you may have in fact seen a lot about air parcels and understand the idea. That's why there's one more lecture in this, this module of the course that's about air parcels. It happens to be exactly the same, literally the same lecture I give ATS 113. If you know about air parcels, it's probably okay to skip it. If you don't know what we mean by an air parcel and what its properties are and so on, go ahead and watch it. It's a very short lecture. Frankly, I suggest you watch it in either way. Okay? Anyway, so there'll be one more lecture explaining this idea of air parcels, because this is a powerful idea in atmospheric sciences for understanding the forces at work in the atmosphere and so on. Alright, now I told you that there were a few more forces that your book doesn't actually mention, and you know, the reason why they don't really mention them is because, I mean, they're interesting in atmospheric dynamics, you know, the fluid mechanics of the Earth's atmosphere and so on, especially under certain conditions, but they're generally not conditions that are hugely relevant for wind power conditions. I mean, for example, there's a very strong centrifugal force that's at work in a tornado. It's one of the very strong forces that are controlling how air parcels are moving around the center of the tornado. Are you planning on generating a lot of wind power for your turbine at a tornado? Probably not. So we're not going to need to worry about centrifugal force that much in this kind of application. And there's other examples of this that are interesting in different contexts, but they aren't necessarily important in the context of wind power. Whew, we made it to the end of this very long lecture. Before we go, let you loose on that air parcels lecture, let's go ahead and have 3 more quick questions. Question 10. Which is the only force in the atmosphere that can start the wind? The pressure gradient force, friction, the Coriolis force, or apparent gravity? Oh, I don't know that I ever actually said which one could start the wind. You'll have to think about what forces or what they're all doing and come up with an answer to that. Make a choice from those 4 options, get a little feedback before you move on to question 11.